Okay, so good day everyone. So for today, what we're going to discuss about materials requirement planning. So MRP or materials requirements planning is a method for determining the materials and components necessary for the production of a product. So it comprises of three major steps, no? Inventorying the available materials and components, determining which extra ones are required, and finally arranging their manufacture or acquisition. When we say MRP, MRP, which is accomplished mostly through a specialized software, no, ensures that the appropriate inventory is accessible for the manufacturing process exactly when it is required and at the lowest feasible cost, no, because thus MRP enhances the effectiveness, adaptability, and portability of manufacturing operations. It can increase worker productivity, enhance product quality, and reduce materials and labor expenses. Materials resource planning also enables producers to respond to growing demand for their products more rapidly and to minimize manufacturing delays and inventory stockouts that can result lost consumers, so which contributes to the revenue growth and stability. And to give us more details about the topic, let us all welcome our presenter. Go ahead, ma'am.
Thank you po, Dean. So, yeah, good afternoon, classmates. So, my topic is about material requirements planning. So, it's about supply and demand planning and control. So, for our learning objectives, today we'll be going over the following. We'll be explaining what material requirement planning is. We will be we could we'll be able to understand more about how MRP system is structured, and we'll be able to analyze an MRP problem and evaluate and compare MRP lot sizing techniques. So first, understanding material requirements planning. So what is MRP? MRP, meaning material requirements planning, it's the logic for determining the number of parts, components, and materials needed to produce a product. Our emphasis in this chapter is on material requirements planning, which is the key piece of logic that ties the production functions together from a material planning and the control view. So it is based on dependent demand. It is caused by the demand for a higher level item. So like I'll be showing some of the fields or industries where MRP can be used. So here are some of the industry applications and expected benefits of MRP. Industry type, assemble to stock. These are the component parts that's I mean stock in inventory to satisfy customer demand. So finished product, I mean the component parts into a finished product. So examples are watches, tools, appliances. Make to stock, these are standard stock items carried in anticipation of customer demand. So examples are piston rings, electrical switches. Assemble to order, a final assembly is made from standard options that the customer chooses. Examples, trucks, generators, motors. Make to order, items are manufactured by machine to customer order. Most likely, these are industrial orders like bearings, gears, fasteners. Engineer to order, these are the fabricated or assembled completely to customer specification, such as turbine generators, heavy machine tools. Process, it includes industries such as foundries, rubber and plastics, specialty paper, chemicals, paint, drug, food processors. So those are the examples. Okay. And then let's move on to master production scheduling. So it is a time-phase plan specifying how many of each an item the firm plans to build and when. Generally, it deals with end items. So typically, it's the finished goods items sold to customers, and it is a major input to the MRP process. If the end item is quite large or quite expensive, however, the master schedule may schedule major sub-assemblies or components instead. Just a reminder, all production systems have limited capacity and limited resources. So this presents a challenging job for the master scheduler. So since there could be some technicalities or difficulties in terms of the scheduling, here are some things to ensure good master scheduling. The master scheduler or the human being must include all demands from product sales, warehouse, replenishment, spares, and interplant requirements. Number two, never lose sight of the aggregate plan. Number three, be involved with customer order processing. Number four, be visible to all levels of management. Number five, objectively trade off manufacturing, marketing, and engineering conflicts. Number six, identify and communicate all problems. So here, it's a figure, the aggregate plan, or a table rather, the aggregate plan and the master production schedule for mattresses. I'm just showing an example. So if you can see here in month one, for example, there's a total of 900 mattresses are scheduled. So it's split in different models, model 327, 538, 749. And the next level down, the MRP program that develops detailed schedules showing when each items are needed to make the mattresses. So to summarize the planning sequence, the aggregate operations plan discussed in previous chapters specifies product groups, and it does not specify exact items. So I'll be showing you more details about this. Here, it's connected to the master production schedule. So it's a time-phased plan specifying how many of each and item the firm plans to build and when. So for example, the aggregate plan for a furniture company may specify the total volume of mattresses it plans to produce over the next month or next quarter. Time fences, which is related to MPS as well. The purpose of this is to maintain a reasonably controlled flow through the production system unless some operating rules are established and adhered to. The system could be chaotic and filled with overdue orders and constant expediting. The question of flexibility within a master production schedule depends on several factors. Take note of this: production lead time, commitment of parts and components to a specific end item, relationship between the customer and vendor, amount of excess capacity, and the reluctance or willingness of management to make changes. So I'll be showing an example of a master production schedule time fence. So here, this is the master production schedule time fences. We have the capacity, the number of weeks, on the x-axis, frozen, slushy, and liquid. So if you can see firm customer orders on the left part and then forecast and available capacity. Under these rules, frozen could be defined as anything from absolutely no changes in one company to only the most minor of changes in another. In slushy, it may allow changes in specific products within a product group, so as long as parts are available. And in liquid, it may allow almost any variations in products with the provisions that capacity remains about the same and that there are no long lead time items involved. Some firms use a feature known as available to promise. So you may have some questions about what is available to promise. So it's simply a feature of MRP It's a feature of MRP systems that identifies the difference between the number of units currently included in the master schedule and the actual firm or the customer orders for items that are master scheduled. So in this feature, it identifies the difference between the number of units currently included in the master schedule and firm customer orders. So for example, assume the master schedule indicates that 100 units of a specific model, or let's say a model of 538 mattresses are going to be made during week 7. If firm customer orders now only indicate that 65 of those mattresses have actually been sold, the sales group has another 35 mattresses. So these 35 mattresses are the ones that are available to promise for delivery during that week. So if we're just going to do the simple math, 100 minus 65, so 35 is the available to promise. So this can be a powerful tool for coordinating sales and production activities. Okay, so next, we have 4 under material requirements planning system structure. This is the planning portion of manufacturing activities and most closely interacts with the master schedule, bill of materials file, inventory records file, and output reports as shown here. So this is the overall view of the inputs to a standard material requirements. If you can see, the master production schedule states the number of items to be produced during specific time periods. We have the bill of materials file here. It identifies the specific materials used to make each item and the correct quantities of each. And on this section, the inventory records file, this contains data such as the number of units on hand and on order. These 3 sources, the master production schedule or MPS, bill of materials or BOM, and inventory records file become the data sources for the material requirements program. So it's in the these are the main data sources for the whole MRP, which expands the production schedule into a detailed order scheduling plan for the entire production sequence. So let's go first to demand for products. So product demand for end items comes primarily from 2 main sources. The first is known customers who have placed specific orders, such as generated by sales personnel or from interdepartment transactions. So these orders usually carry promised delivery dates. There is no forecasting involved in these orders, simply add them up. And the second one is the aggregate production plan, which reflects the firm's strategy for meeting demand in the future. The strategy is implemented through the detailed master production schedule. And in addition to the demand for end products, customers also order specific parts and components either as spares or for service and repair. These demands are not usually part of the master production schedule. Instead, they are fed directly into the material requirements planning program at the appropriate levels. And then the next one is the bill of materials or BOM. So it's often called the product structural file or product tree because it shows how a product is put together. It contains the information to identify each item and the quantity used per unit of the item of which it is part. So here, basically it's still because it's part of the exhibit 21.4. So here it is, bill of materials file. But I still have another figure to show. So here, for the bill of materials, this is what I've mentioned earlier, product structure tree. For product A, it is made up of 2 units of part B, this one, and 3 units of part C, so 2 and 3. Part B is made of 1 unit of part D and 4 units of part E. Part C is made of 2 units of part F, 5 units of part G, and 4 units of part H. So bill of materials files often list parts using an indented structure. This clearly identifies each item. So basically it's identified here, and in which it is assembled, because each indentation signifies the components of the item. So a comparison of the indented parts in Exhibit 21.5 B and with the item structure in 21.5A, the one that I've shown earlier, shows the ease of relating the two displays. From a computer standpoint, however, storing items in indented parts list is very inefficient. So with this modular bill of materials, it's basically the term for a buildable item that can be produced and stocked as a sub-assembly. What else? Let me just go back to this one. So low level coding: if all identical parts occur at the same level for each end product, the total number of parts and materials needed for a product can be computed easily. Next is inventory records. So the inventory records file can be quite lengthy. So here it is. It's an product hierarchy expanded to the lowest level of each item. So consider product L, this one, L, shown in Exhibit 21.6A. Notice that item N, for example, occurs both as an input to L and as an input to M. So therefore, it needs to be lowered to level 2, which is in here, to bring all ends to the same level. If all identical items are placed at the same level, it becomes a simple matter for the computer to scan across each level and summarize the number of units of each item required. So here, 21.7, this part, inventory status record for an item in inventory. For example, we may want to know what sub-assemblies are generating the requirement for a part that we order from a supplier. The MRP program allows the creation of a PEG record file, either separately or as part of the inventory record file. Okay. So the last one is MRP computer program. The process of calculating the exact requirements for each item managed by the system is often referred to as the explosion process. Working from the top level downward in the bill of materials, requirements from parent items are used to calculate the requirements for component items. And of course, consideration is taken of current on-hand balances and orders that are scheduled for receipt in the future. Just a key idea: MRP programs are integrated into ERP systems offered by companies such as SAP and Oracle. So here are general descriptions of MRP explosion process. Let me just proceed with the next slide. So typically, the explosion calculations are performed each week or whenever changes have been made to the master schedule. Some MRP programs have the option of generating immediate schedules called net change schedules. So next is net change systems. This is MRP systems that calculate the impact of a change in the MRP data. What are those? The inventory status, BOM, or material schedule. BOM, again, is the bill of materials. Net change systems are activity-driven, and requirements and schedules are updated whenever a transaction is processed that has an impact on the item. Net change enables the system to reflect in real time the exact status of each item managed by the system. So, an example using MRP. Here, meters used on single-family homes are of two basic types for different voltage and amperage ranges. In addition to complete meters, some sub-assemblies are sold separately for repair or for changeovers to a different voltage or power load. So here are some of it: forecasting demand, bill of materials, developing a master production schedule, inventory records, performing MRP calculations. So let's go first to forecasting demand. Demand for the meters and components originates from two sources. We have this regular customers that place firm orders in advance based on the needs of their projects, and other typically smaller customer that buy these items as needed. So here we have meter A and meter B, and then sub-assembly. So using one of the usual techniques described in the previous chapter and past demand data, this one shows the requirement for meters A and B and sub-assembly D for a 3-month period. So that's month 3, 4, 5. There are some parts used to make the meters. In order to keep our example manageable, we are not including them in this example. So we will be discussing it further on the next items. So developing a master production schedule. For meter and component requirements, assume that quantities to satisfy the known and random demands must be available during the first week of demand. This assumption is reasonable because management, in our example, prefers to produce meters in a single batch each month rather than a number of batches throughout the month. So in this table, it shows a master schedule to satisfy demand requirements as specified. It shows the trial master schedule that we use under these conditions with demand for months 3, 4, 5. The schedule we develop should be examined for resource availability, capacity availability, and so on, and then revised and run again. So you would be considering different factors before you will be able to revise and run it again. Next is again, bill of materials, product structure. The product structure for meters A and B, as shown here, is a typical way using low level coding, as what was discussed previously, in which each item is placed at the lowest level at which it appears in the structure hierarchy. So from the product structure, notice that part D, or the transformer, is used in sub-assembly C, which is used in both meters A and B. In the case of meter A, an additional part D is needed. The 2 in the parenthesis next to D, when used to make a C, indicates that 2 Ds are required for every C that is made. The product structure, as well as the indented parts, indicates how meters are actually made. First, sub-assembly C is made, and potentially these are carried in inventory. In this, it shows the sub-assemblies and parts that make up the meters and shows the numbers of units required per unit of parent in parentheses. Inventory records. For inventory records, it would be similar to those shown here in and on this figure. Additional data such as vendor identity, cost, and lead time also would be included in these data. For this example, the pertinent data include the on-hand inventory at the start of the program run, safety stock requirements, and the current status of orders that have already been released. So safety stock is a minimum amount of inventory that we always want to keep on hand for an item. For example, for sub-assembly C, we never want the inventory to get below 5 units here. So it's the safety stock. We never want that this would be below 5 units. So you also see that we have an order for 10 units for of meter B that is scheduled for receipt at the beginning of week 5 here on order on this column. And then another order for 100 units of part B here is scheduled to arrive at the beginning of week 4. So, ganun siya. Parang they have the inventory, they have the record in terms of the all of the units that needs to be delivered or expected to arrive. Performing the MRP calculations, conditions are now set to perform the MRP calculations. Here, there's actually a calculation regarding those, but I won't dig deeper regarding that. But basically it's more of just um balancing and checking the stocks, and then how much stocks are expected to be produced, how much do you need to allot so that you would be able to utilize it for the next coming weeks. So the following analysis explains the logic in details. So the MRP record, this is kept for each item managed by the system. And this record contains gross requirements, scheduled receipts, projected available balance, net requirements, planned order receipts, and planned order releases data. So a net requirement, this is the amount needed when the projected available balance plus the scheduled receipts in a period are not sufficient to cover the gross requirement. Next is about lot sizing in MRP systems. So in here, we'll be determining lot sizes in an MRP system. It's kind of complicated, and it's really a difficult problem in terms of checking the lot sizing here in MRP. It's part of the quantities issued in the plant order receipt and plant order release sections of an MRP schedule. So let's go first to lot for lot. For lot, it is the most common technique. It sets planned orders to exactly match the net requirements. It produces exactly what is needed each week with no inventory carried over into future periods. So here, the net requirements in this column, if you can see, the net requirements are given in column 2. Oh, sorry. Here in column 2, because the logic of lot for lot says the production quantity, which is here in column 3, will exactly match the required quantity, which is here the net requirements, that there will be no inventory left at the end. So this is the ending inventory. So it should be 0. So the net requirements and the production quantity should be equal. So without any inventory to carry over into the next week, there is 0 holding cost. So this would be 0. However, for lot, it requires a setup cost each week. So you can see here on the column 6, this is the setup cost. Incidentally, there is a setup cost each week because this is a work center where a variety of items are worked on each week. So this is not a case where the work center is committed to one product and sits idle when it's not working on that product, in which case only one setup would result. So with that being said, lot for lot causes high setup cost. So for economic order quantity, or the EOQ model, It uses an estimate of total annual demand, the setup or order cost, and the annual holding cost. Here is a table of the economic order quantity run size for an MRP schedule. This shows the MRP schedule using an EOQ of 351 units. The EOQ lot size in week 1, or in here in the first row, is enough to meet requirements for weeks 1 to 5. So for this, from week 1 to week 5, it's the requirements are just enough. And a portion of week 6. So there's still a portion left for week 6. Then in week 6, another EOQ lot is planned to meet the requirements for week 6 through 8. So this one again, 351. So if you'll notice that the EOQ plan leaves some inventory at the end of week 8. So ending inventory for week 8, there's still left na they can use for the succeeding weeks. They can carry it forward into the next or preceding weeks. So that's the EOQ model. Next is the least total cost. It is a dynamic lot sizing technique that calculates the order quantity by comparing the carrying cost and the setup cost for various lot sizes, and then selects the lot in which these are most nearly equal. So let me show you the least total cost run size for MRP schedule. So the best lot size is 335 here on 1, 2, 3, 4 on the 5th row of the week, because a $38 carrying cost and a 47 ordering cost. This is closer than the 56.75 here and the $47. This lot size covers requirements for weeks 1 through 5. Unlike EOQ, the lot size covers only whole numbers of periods. Based on the week 1 decision to place an order to cover 5 weeks, we are now located in week 6 here. So the problem here is how to determine, I mean determining how many weeks into the future we can provide from here. And then next is the least unit cost. It is a dynamic lot sizing technique that adds ordering and inventory carrying cost for each trial lot size and divides by the number of units in each lot size, picking the lot size with the lowest, again with the lowest unit cost. So here, this one, the lowest unit cost, moment. So the top half of the previous figure calculates the unit cost for ordering lots to meet the needs of weeks 1 through 8. Note that the minimum occurred when the quantity 410 ordered in week 1 was sufficient to cover weeks through 6. The lot size planned for week 7 covers through the end of the planning horizon. The least unit cost run size and total cost are shown in the bottom half of 21.6. Actually here on this part. And then lastly, choosing the best lot size. Using the lot for lot method, the total cost for the 8 weeks is $376. The EOQ total cost is $171.05. The least total cost method is $140.50. The least unit cost is $153.50. The lowest cost was obtained using the least total cost method of 140.50. If there were more than 8 weeks, the lowest cost could differ. So it's still based on the figure that I have shown earlier. The advantage of the least unit cost method is that it is a more complete analysis and would take into account ordering or setup cost that might change as the order size increases. If the ordering or setup cost remain constant, the lowest total cost method is more attractive because it is simpler and easier to compute. Yet it would be just as accurate under that restriction. So yeah, that's it for my report. Thank you so much for listening.
Okay, so again, MRP is a crucial to the efficacy, productivity, and ultimately probability of a manufacturing business. No? So without the proper raw materials and components on hand, procedures cannot hope to meet the ideal cost and quality product demand. So they will also be less able to modify production in response to swings and demand. The MRP can also improve the predictability and the smoothness of later stages of production, such as assembly and packaging, by eliminating the majority of inventory uncertainty and reducing the time required to handle it. MRP is useful in discrete manufacturing where the final products are distinct items that can be counted, such as bolts, sub-assemblies, or automobiles and process manufacturing, which result in bulk products and cannot be counted separately or broken down into the constituent parts, such as the chemicals, soft drinks, and detergent. So the major purpose actually is to ensure that materials and components are readily available during the production process and that manufacturing occurs on time. No additional advantage, of course, shortening client lead times on enhancing customer satisfaction, decrease cost inventory, and so on. Okay, so I think no, that's it. Actually, MRP is widely utilized by manufacturers and has unquestionably been an important factor in the expansion and widespread availability of affordable consumer goods rather, which has therefore enhanced the standard of living in the majority of countries. So without a mechanism to automate the complex calculations and data management of MRP processes, it is improbable that individuals' factories could have expanded operations as rapidly as they did in the 50 years since the introduction of the materials resource planning software. Okay, so that's it.